Okay, so this really falls in the category of things I teach, but it's really kind of like a modern kind of way to push more information on the students, really. But I'm going to go ahead and sort of give you the overview because I think it is kind of important that you know it. I might ask you a couple of simple kinds of questions from this, but you really should just look at the section in your book on organic compounds, the very last section in this chapter. So there are compounds we call hydrocarbons. And the hydrocarbons contain hydrogen and carbon, things that have C and H. Okay, um, they are classified a couple different ways. The first thing that we notice in hydrocarbons is like how many carbons there are in the compound. So if there are if there's just one, then it's going to be prefixed by meth, and then the last part, I don't like the drug, but that's going to be followed by an A and E. So it's a methane. So methane is actually CH4, and I'll draw it over here so you can get an idea. CH4. The structural formula for it looks something like this. Okay. Now ethane has two carbons in it. Now every carbon can make four bonds, and this is typical the way we think in organic chemistry. Every carbon can make four bonds. So this methane has four bonds to it. Now when I want to draw ethane, I can draw it like this. It has two carbons in it. Now here's the deal. Hydrogen can only make one bond. And so it ends up being that the carbons have to be bonded together. They're always in the middle of the structure. So ethane actually looks like this. Now remember I said every carbon holds four bonds, right? So there's 1, 2, 3, and then one of them's to the carbon adjacent, and then there's 1, 2, 3. And again, they're sharing that one bond in between, so that's the 4 for each. So this is methane, and this is ethane. Now let's go ahead and try a little experiment here, right? Why don't you draw the structure for butane, right? So you can get an idea how this works. All the carbons in butane will be lined up. Now I didn't tell you this, but I think you kind of inferred it already. This is 1, 2, 3, etc. all the way down the line. So why don't you draw butane? I'm going to actually pause it and you can jump back in, and then you can see if you matched my structure. All right, so this is butane. It's got 4 carbons in a row, right? And it's surrounded by hydrogens. If you're careful and you count, right, every one of those carbons has 4 bonds. So those are the alkanes. They're also referred to as saturated compounds because they have as much hydrogen in the compound as you possibly can for the bonds. Now, if you remove 2 hydrogens, then what you can do is you can make an alkene. And this creates a situation where you have something called a double bond. So if I take 2 carbons like this, put them next to each other, and I draw a double bond like this. That's how we would represent not just one pair of electrons, but 2 pairs of electrons in between the 2 atoms holding it together. And yes, the bond is stronger if you're thinking that. How many hydrogens can I put there? Well, each carbon already has 2 bonds, so I can just basically I can do this. Now, when you have a double bond, the suffix becomes ene. So this is ethene. But unfortunately, the probably more common way that you hear this is the older nomenclature. It's ethylene. So this is sort of a common name, right? And then ethene is the systematic name, but they both represent the same thing. And this actually is the hormone that plants use to go and produce color in their skin. It's the ripening hormone. It helps them to mature. Tomatoes in like cold storage, when they're green, one of the ways they get them to all be red at the same time is blow ethylene gas over the top of them. Okay, now if I get rid of 2 more hydrogens, right, then I'm going to have a compound that looks like this. Put a triple bond in there, right? I have hydrogens and hydrogens. This is known as a triple bond, right? And this is ethyne. And again, if you count the bonds on the carbon, there's still 4 bonds, right? So now you're like an expert in drawing hydrocarbons, because there really isn't much more to it than this, for alkanes, right? And alkenes and alkynes. Now, having said that, oh, by the way, ethyne also has a very recognizable common name, and it's known as the acetylene. It's the welder's gas. So unfortunately, acetylene, right, looks like it has a double bond, but that's really a triple bond. It got its name because if you took like acetic acid and you decomposed it in the right way, it had 2 carbons. So this ACET prefix stands for 2 carbons in the older sort of common nomenclature that we have surrounding all of chemistry. Really, we have lots of common names for things. Okay, so these are not functionalized. These are straight hydrocarbons, and then they have this thing that your book refers to as functionalized hydrocarbons, right? And a functionalized hydrocarbon is a hydrocarbon that doesn't just have carbon and hydrogen in it with single bonds, but it has a part of the molecule that gives it a function, okay? And you know, this is just the tip of the giant iceberg of what we call organic chemistry. But it's really fun, I'll be honest with you. So alkenes and alkynes have functional groups, and those functional groups are the double and triple bonds. And they're functional because, like if you were to do chemical reactions, for example, you could form alkanes out of them by adding hydrogens to them. So that's the function of that double and triple bond. You can also add other things to them as well. If you have an OH, right, that is what we refer to as an alcohol. So, for example, ethyl alcohol. Now, you'll recognize this, I'm drawing ethane. But I remove a hydrogen and instead I put an OH on here. Now, remember the rule of carbon always has to have 4 bonds. Well, it turns out oxygen always has to have 2 bonds. And so that's the structure for ethanol. And you can see all I did is took ethane and added the OL from the alcohol name. You don't need to know that part of the nomenclature. I just thought it helps to see in context. There's also amines, which contain NH2 groups. So if I were to draw the amine version, right, I'd be just drawing ethane again. And then I would put an N. And nitrogens can take 3 bonds like this. Okay. And unfortunately, this becomes known as not, like you would think there'd be like a cute way with the OL, but there isn't. It's ethane amine, and just add the name amine to the end of it. But they get rid of the E, so it becomes ethanamine. Okay, so there's amines, and there's also carboxylic acids. That's the organic acid functional group. That's the most common. It's the acid functional group that we get in acetic acid and things like that. And then there's aldehydes. Aldehydes have this sort of general structure to them. Again, I'd like you to know the names of these functional groups and maybe the formulas the way they're shown here, but you don't need to be able to draw all the structures. But this would be an aldehyde. Again, carbon can take 4 bonds. This is formaldehyde, the thing they use for preserving dead things in biology. Again, each hydrogen has 1, each carbon has 4, right? And the oxygen has 2, so it's following all those rules that we talked about before. And then the last type of functional group that I kind of want you to know the name of and the general formula, right, is a ketone. And a ketone is actually just like an aldehyde, but it doesn't have any hydrogens on it. So, for example, this could be part of a ketone. Well, let's just draw the whole ketone. This is a ketone. Okay, that's actually unfortunately known as acetone. You remember I said ACET means, right, two carbons, but this goes all the way back to the Middle Ages, like 1500s, and they were doing experiments, and they were able to distill this material out, and they thought it was related to acetic acid, but it was really a new compound, and then that became known as acetone. So that just kind of stuck for, what is it, 2020? So like 500 years. So anyways, they started early, so they get to keep the name, I guess. So, all right, so that's functionalized hydrocarbons, and those functional groups give them very specific kind of properties. Just side note, aldehydes are things like vanilla, and camphor would be a ketone, if I remember right. So they have sort of these sort of distinct aromatic-y kind of smells, right? Because they thought that these great smells and things were coming from life or living things, right, all the time, then they called those things organic compounds. It turns out there's lots of things that are organic that don't smell good and aren't nice and don't do good things for you, but they didn't know that. And then there's inorganic, and those are the things like minerals and things that they didn't think were like parts of living. They were part of like the earth and the ground and minerals, whereas these organic compounds were part of what we call life, right? They're part of the things that make animals and people go. Okay, so that's kind of where the name comes from. It's kind of old, but and not entirely accurate anymore, but it's still stuck. So there you go. Just like acetone for 500 years. All right, so that's the end of this chapter. I put less weight on this organic nomenclature or organic compound section, but I still want you to know some of the basic information.